Okay, let's talk about AI. Seriously, it feels like every single week there's a new headline telling us that these things are getting smarter, faster, practically thinking for themselves. We see demos where they solve coding problems, write essays, even generate these detailed explanations that look like a human working through a tough challenge. There's this growing feeling, that the newest AIs, especially the ones designed to show their work generating step-by-step thought processes, have somehow cracked the code on true intelligence. Like they've moved beyond just pattern matching and can actually reason. But is that picture? Well, is it the whole story? Or is something much more complex and maybe even counterintuitive happening under the hood? Today we're taking a deep dive into a really fascinating and frankly pretty surprising new study from researchers at Apple. They decided to put these sophisticated AIs to a different kind of test. Not the usual broad benchmarks the AI might have seen in its training data, but something much more controlled and fundamental. Classic logic puzzles. And what they uncovered challenges a lot of assumptions about how these powerful AIs actually think, if they think at all.
That's right. The paper we're unpacking today is titled The Illusion of Thinking. Pretty direct, huh? It gets straight to the point by examining what the authors call large reasoning models, or LRMs. These are precisely the types of advanced AIs that are specifically built or fine-tuned to produce detailed sequences of intermediate steps, like the populate chain of thought approach, before giving a final answer. Think of models they tested like Claude 3.7 to Sonnet Thinking, DeepSeek R1, and some specific versions of OpenAI's O3 models. The core puzzle this research sets out to solve for us is this. While these LRMs can seem incredibly capable on many tasks, often outperforming older models, it's not truly clear why. Are they genuinely performing logical deduction like a human solving a new problem by applying rules? Or are they just exceptionally good at statistical pattern matching, stringing together words and ideas that look like reasoning because they've seen similar structures across, vast amounts of internet text during training? As the study points out, standard tests like asking for code or solving complex math problems might not be the best way to find out, because the AI could potentially have encountered similar problems or parts of their solutions in the massive data set they learned from.
Yeah, it's like giving a super smart student a test question they accidentally saw the answer to beforehand. They might get it right, but you don't actually know if they understood how to solve it, or if they just remembered the answer. This study was designed to avoid that trap. They built a test where the AI couldn't possibly have just memorized the solution. And what they found was genuinely surprising. It turns out when faced with these controlled logic problems, AI reasoning hits a really distinct wall. Performance doesn't just slowly degrade as things get harder, it completely collapses. And here's something wild. Sometimes the older, less thinky versions of these AIs were actually better and more efficient than their newer reasoning-focused siblings on simple tasks. Okay, let's really dive into the details of these counterintuitive results from the study.
So, to truly test whether these AIs could reason based purely on rules and not just, regurgitate something similar they'd seen before, the researchers needed a very specific environment. Their solution, as you mentioned, was brilliant. Controlled puzzle environments. Imagine these as miniature digital labs where the rules are explicit, the starting state is clear, and the goal is well-defined.
Puzzles. Okay, why puzzles specifically?
Well, the paper gives several compelling reasons. First, they allow for incredibly precise control over difficulty. You can add just one more disk, one more person, one more block, and that single addition predictably increases the complexity of the optimal solution path. This lets you test how the AI scales with difficulty very deliberately.
Right, you can turn the dial up bit by bit.
Exactly. Second, as we touched on, it minimizes the chance that the AI has simply memorized a similar problem during training. These puzzle instances were generated specifically for the study.
So fresh problems.
Fresh problems. Third, solving these requires only the explicit rules given. There's no need for outside world knowledge, common sense, whatever that is, for an AI or external data. It's purely about applying logical steps based on the rules provided.
Makes sense.
And this is key. Fourth, because these puzzles have clear, verifiable moves, the researchers weren't just guessing what the AI was doing. They could analyze the AI's step-by-step process, its thinking trace, and see if each proposed move followed the rules and moved towards the goal.
Yeah, makes total sense. It strips away all the ambiguity and just asks, Can you follow these rules to reach this goal?
Hmm. So what specific logic puzzles did they use? I think you mentioned some classics.
They did. They picked some classic ones that are easy to understand visually or conceptually. There's the famous Tower of Hanoi.
Oh yeah, the discs on pegs thing.
Right. You have discs of different sizes on pegs, and you have to move them to another peg, one at a time, never putting a larger disc on a smaller one.
Got it. What else? Then there's checker jumping, a simpler one-dimensional puzzle about swapping positions of colored checkers on a line using slide and jump rules.
Okay.
They also used river crossing puzzles, the type like getting missionaries and cannibals across a river where the rules prevent certain dangerous combinations.
Right. The classic logic setup, make sure nobody gets eaten.
Pretty much. And finally, Blocks World, which involves stacking blocks in a specific order to match a target configuration, like digital Lego building with rules.
The real power of using these, as the study highlights, is how easily you can dial up the difficulty, right?
Exactly.
Adding one more disc to Tower of Hanoi doesn't just add one step, it exponentially increases the minimum number of moves required. Adding one more person to the river crossing puzzle can drastically change the possible valid paths. This variable complexity was crucial for seeing how the AI's performance changed as the problems got harder, keeping the type of logic required consistent.
And this is where the study delivered its first major shockwave. Across all the different puzzles they tested, the AI's accuracy didn't just gradually decline as the problems got harder.
Yeah.
That would be expected.
Yeah, you'd think it just gets worse slowly?
Instead, it completely collapsed to zero accuracy beyond a certain, surprisingly low difficulty level for every model they tested. And that includes the most advanced thinking models like Claude 3.7 Sonnet Thinking and DeepSeek R1. The study calls this a fundamental limitation. Forget a gentle slope of declining performance. What they found was a sheer cliff face.
Wow.
Once the problem complexity crossed a specific threshold, the AI's ability to solve it just vanished entirely.
0% accuracy. That's
Yeah.
wild. It's not just getting some wrong, it's getting all of them wrong past a certain point.
Yeah.
And that critical point was different for different AI models. But for any given AI, once you hit that level of complexity, game over. What's even more interesting is how this played out across different levels of difficulty when they compared the thinking models to their older, non-thinking siblings. You mentioned pairs like Claude 3.7 Sonnet Thinking versus just plain Claude 3.7 Sonnet, or DeepSeek R1 versus DeepSeek V3. The study identified what they called 3 regimes of complexity. Let's break that down.
Okay.
First, simple problems. You might expect the AI designed to think more would be better, right? Give it space to work it out.
You'd think so.
But surprisingly, the non-thinking models were often just as good or even better. And they used significantly fewer steps or tokens to get the answer.
Yeah.
It's like basic math facts, say 5 plus 7. You don't need to write down a step-by-step thought process, you just know it's 12. The older AI is faster and more efficient here because it doesn't bother with the extra thinking steps.
Exactly. They just give the answer directly, which works perfectly for easy tasks. Much more efficient. Then you have the second regime, medium problems.
Okay.
This is where the thinking models shined. The extra steps they generated, the chain of thought process, seemed to genuinely help them navigate the complexity. They could find solutions to problems that completely stumped their non-thinking counterparts.
So like a multi-step algebra problem. Writing down each step, showing your work, actually helps you solve it correctly.
Precisely. The thinking AI benefits from that explicit process here.
Okay, so simple problems. The non-thinking AI is fine, maybe better. Medium problems. The thinking AI is better. What about the third regime? The hard stuff.
The third regime is the collapse zone we talked about, hard problems. Here, both types of models failed completely. The extra thinking steps of the LRM didn't help at all.
So the thinking didn't save it.
Nope. It's like a math problem so incredibly complex, or maybe even impossible with the given information, that no amount of writing down steps or thinking harder is going to get you to a solution. The AI hits its fundamental limit regardless of its approach. And another really counterintuitive finding emerged when they looked at how much effort the AI seemed to be putting in. They measured this by the number of thinking tokens it generated, essentially, how much it wrote down for its internal process.
Okay, how much work it was doing.
Yeah. As problems got harder, up to a point, the AI did increase its effort, generating more detailed thinking steps. Like, it was trying harder.
Makes sense.
But T, and this is the strange part, as it approached that point where it completely failed that complexity cliff, it surprisingly started generating fewer thinking steps.
Fewer. It gave up.
It seemed to give up, yeah. Even though it had the capacity, the token budget, to keep generating. It's a bit like a student taking a test who gets to a problem that's clearly way too difficult. Instead of trying every possible angle, they just write down less and less, eventually stopping, even if there's time left on the clock.
Huh.
The study interprets this as the AI hitting a fundamental scaling limitation. It doesn't know how to effectively scale its internal process to tackle increasing difficulty. It just kind of checks out.
That's fascinating and a little unsettling. It's not just that it can't solve it, it's that its approach changes as it gets closer to failure. This study really went deep by looking inside the AI's process, which they could do because the puzzles provided clear, verifiable steps. They analyzed these thinking traces or thoughts the AI generated before giving its final answer.
Exactly. They could literally look at the sequence of moves the AI proposed in its internal steps and see if they were valid according to the puzzle rules. And analyzing these traces revealed different patterns depending on the difficulty level, especially when they zoomed in on a model like Claude 3.7's Sonnet Thinking. For simple problems, you might expect the AI to quickly figure out the correct solution and then just state it.
Yeah, find the answer, say the answer. Done.
But the study found something unexpected. The AI often found the correct solution early in its thinking process, but then kept generating more steps, exploring incorrect solutions afterward.
Why?
The study aptly describes this as overthinking. It's like you solve a simple puzzle in 3 moves, know you're done, but then spend the next minute trying random extra moves that mess things up.
So it solves it, then potentially unsolves it by thinking too much.
Sort of, yeah. Or at least wastes effort and introduces potential errors after the fact. For medium problems, the thinking traces showed a different pattern. Here, the AI often explored many incorrect paths first, trying different sequences of moves, and only found the correct solution much later in its generated process. This is more like what you might expect when tackling a moderately tricky problem. You try a few things that don't work before you hit on the right approach.
That sounds more like actual problem solving.
Yeah.
Trial and error.
It looks more like it, yes.
Yeah.
But for hard problems, the thinking traces were just broken. The AI simply failed to generate any correct step or make progress towards the solution throughout its entire process.
Just noise, basically.
Pretty much. This detailed look inside the AI's mind suggests real limitations in its ability to efficiently search for solutions, self-correct when it makes a wrong turn, or even recognize when it's found the right answer on simple tasks.
The overthinking on simple problems is particularly strange. It's like it can't tell when it's done, or it just feels compelled to keep generating text even after it's solved the problem. And the study uncovered some even deeper inconsistencies that are truly puzzling and raise fundamental questions about what's going on. Get this. For the Tower of Hanoi puzzle, the researchers didn't just give the AI the rules. They gave it the exact, step-by-step algorithm that a human would use to solve it perfectly.
The actual instructions.
The actual instructions. You would think surely the AI could just follow the instructions, right? Like running code.
You would absolutely think that.
But astonishingly, giving the AI the explicit algorithm did not improve its performance.
No improvement.
None. It still failed at roughly the same level of complexity as when it had to figure out the solution all by itself. It's like giving someone a detailed recipe for baking a cake, listing every ingredient and step, and they still can't bake it properly, failing at the exact same point they would have if they just tried to guess how to make it.
Wow.
This suggests a profound limitation in following precise, logical instructions, or verifying its own steps against a given procedure.
That particular finding is one of the most striking because it really flies in the face of the idea that these models are good at processing and applying information. It suggests there's a disconnect between understanding text like reading the algorithm and actually applying it logically step by step within a constrained environment.
Yeah. And there was more weirdness.
Yeah.
Inconsistency.
Oh, yeah. Another deeply puzzling finding was the significant inconsistency in performance across different types of puzzles. An AI might handle a relatively complex Tower of Hanoi puzzle, requiring many moves quite well, making dozens or even, I think, up to 100 correct steps in some cases.
Great.
But then it could struggle immensely with a seemingly simpler river crossing puzzle that requires far fewer total moves, getting stuck after only a handful of valid steps.
So it's great at one type of logic, but terrible at another, even if the second one looks easier on paper.
Exactly. The study suggests a possible explanation for this variation. Perhaps the AI's performance is heavily influenced by what kind of puzzles it's seen examples of during its training. River crossing problems with varied numbers of people might be less common or less structured in typical training data than examples related to Tower of Hanoi, which is, discussed a lot online in computer science contexts.
So it comes back to pattern matching again.
It points back to that idea, yeah, that the AI might be relying more on pattern matching against familiar problem types rather than applying truly generalizable logical reasoning that works universally across different problem structures.
Okay, so let's pull this all together. What does this actually mean?
Well, let's bring this back to you, the listener. Why does this research matter if you're interacting with, building with, or simply curious about advanced AI? This study provides concrete evidence that even AIs marketed as having reasoning capabilities have fundamental, sharp limits, especially when faced with increasing problem complexity based purely on logic. They aren't demonstrating true, flexible, generalizable reasoning that scales smoothly to novel logical tasks of varying difficulty. They hit a wall.
So the thinking isn't really thinking in the way we understand it.
It appears not, or at least not reliably under pressure. What this means in practice is that relying solely on these models for complex multi-step reasoning tasks, think about analyzing intricate data, generating complex code for totally new problems, or aiding in detailed strategic planning could lead to unpredictable and complete failures, especially as the task's underlying logical complexity increases beyond whatever that AI's specific threshold is. It also highlights that current popular benchmarks might not be capturing the full picture of AI reasoning ability. Controlled tests like these logic puzzles are crucial for truly understanding their capabilities and, maybe more importantly, their limitations.
Absolutely. This research isn't about saying AI isn't useful or powerful. It clearly is for many, many tasks. We see that every day. But it's about having a realistic, evidence-based understanding of what they are good at and where they currently fall short, especially in areas that seem like core reasoning. It really underscores that building AI with robust, generalizable reasoning abilities, the kind that work reliably on novel, complex problems, is still a significant open challenge in the field. They might look like they're reasoning, but this study shows there's potentially an illusion of thinking when the logical complexity ramps up. So to recap this deep dive, we saw that AI reasoning on logic puzzles doesn't just degrade, it completely collapses beyond a surprising complexity threshold.
Total collapse.
Sometimes, simpler, non-thinking AIs are actually better and more efficient on easy tasks. We learned that thinking models strangely seem to reduce their effort or give up on problems that are too hard rather than scaling their thinking process.
Yeah, they should not.
They can also overthink simple problems, exploring incorrect paths even after finding the right answer. And perhaps, most puzzlingly, they struggle to follow explicit step-by-step algorithms perfectly and show surprising inconsistency across different types of logic puzzles.
That's a good summary. And building on these findings and the open questions they leave us with, here's something provocative to consider. If these incredibly advanced AIs, models that can generate human-quality text on complex subjects, if they struggle so profoundly with basic logic puzzles, failing to follow explicit rules perfectly or generalize consistently across different problem structures, well, what does that imply about their current ability to navigate the truly novel, abstract, or messy reasoning problems we encounter in the unpredictable real world?
A fascinating thought to leave you with. Thanks for joining us for this deep dive into the surprising and sometimes puzzling limits of AI reasoning.